So still on the diesel engine generator, we are going to be looking at the second part now, which is the electrical part or the generator itself, the part that converts the rotating mechanical energy produced by the engine into electrical energy. So that is this part that you are seeing now. Okay, so this part is attached to the flywheel of the engine, and then it is the part that receives the rotating mechanical energy from the engine, so which will eventually be converted to electrical energy that we actually need from the generator. So this is the complete unit that you are seeing. So we are going to be discussing this part of it, which is the electrical part of the generator. So the components of this electrical part of the generator. First, it is the armature. So the armature is the part that produces the electrical energy that we need. That is the part where we tap our output from. So if it is on the stator, we will get our output from the stator. Okay. Then if it is on the rotor, we will get our output from the rotor by slip rings on the rotor. So we'll see all of these as we go along. So this is one on the stator now. Okay, so this is the armature that is wound on the stator. So you see that in three-phase machines, these windings, they are placed in the stator in three-phase beds that are separated by 120 electrical degrees from one another. So our output is gotten from the stator, the armature. Then we have the field. The field is the part of the generator that produces the magnetic field that will eventually induce the voltage or the EMF, okay, that we so desired into this armature or onto the armature, irrespective of where it is placed in the machine. So there are some machines, like we said earlier, we will have the feed on the rotor, like this one now. Since the armature is on the stator, the feed will be on the rotor. So that one is called a rotating field generator. Okay, so in rotating field generator, the armature is on the stator and we get our power output from the stator. While in some instances, the field will be on the stator, while the armature will be on the rotor, as we said earlier. So that kind of machine is called a stationary field generator. Okay, because the part of the equipment that is producing the magnetic field that we need to induce EMF onto the armature is on the stator and the armature is on the rotor. Then the power that is so produced will be evacuated from the armature via the slip rings that will be on the armature. Okay, so this is the rotor now. So you see these are the field windings on the rotor. Then we have the stator of the generator. Okay, so these are the two major components. If you remember Faraday's law of electromagnetism on how electricity is generated, that if a conductor is made to move through a magnetic field, that EMF is induced on that conductor, or if the magnetic field is made to vary in position with respect to that of the conductor, EMF will be induced in the conductor. So the conductor is the armature, then the magnetic field is the field. Are we getting it? So now this field, as you are seeing it, is not a permanent magnet, it's an electromagnet, which means that we need a source to magnetize, to send the magnetizing voltage, okay, to it, the DC voltage that will magnetize it. So that will now bring us to the third part, which has to do with the exciter and the excitation system. Okay, so the exciter actually provides the magnetization voltage, the voltage that is needed by the field to be magnetized to produce, so that it can produce the magnetic field, okay, that will eventually induce the EMF onto the stator. Those are the functions, and these are the three basic parts that we have. Though there are two, the other parts, they are just there to assist the generator or the major components to perform their functions. Okay, so we have the protection system that helps to ensure that the equipment is protected against some stringent operational conditions or conditions that will cause damage downstream the generator or even within the generator itself. So we have protection system that looks at the overall equipment, see if these things are developing, warn us, and even shut the equipment down. So we are going to look at them briefly. So this is the alternator. Okay, so we have the field on the rotor, and then the stator is carrying the armature. Are we getting it? Oftentimes, when we are asked what are the parts of the generator, oftentimes you hear us saying we have the stator and the rotor. That is not the part per se, okay? Because the stator houses the major part. The rotor also houses the second major part of the generator, and the major part, they are the armature and the field. So the armature and the field, they can be on any of these parts of the generator, either on the stator or on the rotor. Okay, let us appreciate better this generator, how they function, how they interact, their physics of operation, and how they produce what we actually need, which is the EMF from the generator. So this is a kind of schematic of what we have within the generator itself. So here, this is the armature winding. Okay, so if this armature winding, as we said, is on the stator, that is in a rotating feed generator. Okay, then the feed is on the rotor. The generator is a rotating feed generator. But if it's on the rotor, if this is on the rotor, then this is on the stator, then we have a stationary feed generator. So because most of the generators that will be coming across, they are rotating feed generator, let us just use that to explain the function of the various parts or various components. Then we'll come to how to actually highlight the differences between the various types of generators later. So now you can see that we have the main feed, the main armature of the generator. Okay, so we need a feed to do what? To produce the magnetic field that we need to help us induce the EMF to this armature, and that is provided by the main field of the generator. So it is on the rotor. Okay, so remember we said we need to send in voltage into the main feed to magnetize the feed, since the feed is not a permanent magnet, it's an electromagnet. So we need voltage, a DC voltage, to be sent into it. So that voltage is provided by the exciter unit. So here we have the exciter armature. So the exciter armature is like a small generator. So it produces alternating current that is rectified by this diode rectifier, okay, or rectifier bridge. So this diode rectifier helps to convert the AC produced by the exciter armature. Remember we said the armature, the exciter is like a small generator, which means it has an armature and a field. Okay, so this exciter armature produces that magnetic, that EMF that is sent to the diode plate or the diode assembly that will now convert that alternating current into DC that will eventually be sent to your feed. Okay, so once the feed receives that EMF, that DC voltage, it will now be magnetized. So it will now be turned into an electromagnet. So the feed that will be created as this is rotating, remember it's on the rotor and the engine is turning. As this is rotating, it will now induce voltage onto this the armature. Okay, so all of this will come clearer later. Remember we said we have a field. The armature will need a feed. So this is the feed of the armature. It's a stationary feed. This is rotating armature. Are we getting it? So this is a stationary feed that will be sent, that will have a voltage fed into it to magnetize it, it will in turn induce voltage into the exciter armature. The exciter armature will produce AC that will be rectified and sent to the main feed, which will now induce voltage into the main armature for us to take our supply from. So this is in summary what we have been discussing, and this is how you see it on ground, especially on rotating feed generator. So this is the armature now, okay, which is this. This is where we get our output voltage from. So this is the main feed, which is this main feed here, okay. Remember we said for the main feed to be magnetized, we need to send in DC voltage. That is the function of this exciter. This is the exciter armature, which is this part of the diagram now. So this exciter armature produces alternating current that is rectified by the diode bridge or diode rectifier. You'll see it later. So that will now be sent. The DC is what will be sent through this supply cable to the main feed to magnetize it. Okay, so as this is turning, remember we have the magnet. Once it's magnetized, it will now act as a magnet. As it's turning, it will be cutting all of these conductors, all these armature conductors. That will induce voltage in the conductor for us to have something in the output. Okay, so this is the rotor now, and this is the diode assembly that we talked about that converts what the armature will produce. Okay, the AC that the armature will produce, convert it to DC before it is sent into the feed winding to magnetize the feed. So this is once it has been coupled, this is what you will see. Okay, so this is the main feed, as you can see. Then this is the exciter. This is the exciter feed itself, and this is the one on the rotating part, on the shaft of that is on the rotor, is the armature, as you have it here. So the one that is covering it here now is the field. So that feed is fed with DC voltage from an external source, which could be the exciter, the AVR, automatic voltage regulator. Okay, we will see all of those later as we are going. So now this type of excitation system that we have been discussing, okay, is called the brushless exciter. Are we getting it? Brushless in the sense that there are no brushes carrying power from one unit to another. So you see that the feed is on the stationary part. The armature that produces is on the rotor. Then the diode assembly or the diode plate is also coupled to the rotor and the output is sent to the main feed. So there are no brushes. So this is the brushless excitation system. okay, or we can say the rotating exciter. Then we also have the stationary exciter, okay, or static excitation system. Are we getting it? So in the static excitation system, all the what is needed to feed the main feed, okay, the power that is needed, the DC power that is needed to feed the main feed is sent from the outside, okay, and it comes into the main feed via brushes. Are we getting it? So those are the rotating, that is the static excitation system. So we'll see that later. So this is the diode plate that we've been talking. One end is the positive end, and the other is the positive diode or positive plate, and the other is the negative plate. Okay, so you have the three phases from this armature. The three phases from this armature fed into the exciter, okay, and then the output taken from the exciter also. Are we getting it? So if you look at that connection, you see that one of these plates is positive, right? Then one of these plates, either positive or negative, then let's assume this plate is positive, which means this terminal here is the positive terminal. That would mean that this plate is negative, which means this terminal here is the negative terminal. Okay, then each of these terminals will have the phases to them because they will be connected somehow. Are we getting it? These terminals, they will be connected somehow, which are these connections that you are seeing. Okay, so assuming this one is connected to this one, then one of the phase will come here. This one is connected to this one phase will come here. This is connected to this one phase will go there to make up the three phase. So this is the feed winding, okay, which is what we have here. So this is the rotating excitation system that we are discussing now. So this is coupled onto the end cover of the alternator. That's the part that will cover the front of the alternator itself. Okay, so we see the feed winding, and of course this feed winding will cover the armature winding. So the next is the static excitation system. So the static excitation system, like we said earlier, the exciter is not rotating, it's stationary. It uses semiconductor devices or electronics, okay, to do the conversion as you have here on this diode, as you have on this diode plate, okay, before it is fed to the generator by slip ring. So like we said earlier, the field, that is this field winding, you see it has some wires, you can see, it has to be fed with DC. So that DC voltage, will get that DC voltage from an AVRO like this. So the positive and negative end of the AVRO, as you see it here, F minus, F plus is fed, F plus is fed to the positive end of the exciter feed, and then F minus is fed to the negative end of the exciter feed. Okay, then the input to it is also gotten from the output of the generator, as you can see here. So here we have the input to the exciter. This is one of the legs, and then there is 4, then 3 also to one end of the of the output. Okay, so to this particular spot. Okay, so it is taken from face to face, which is middle, the middle of it, which means that if we are having 415 face to face here, from the output of the generator, the middle connection of it, okay, we'll be having 220 volts, which is now fed to the AVR. So the AVR output comes to the exciter feed. The exciter feed will be magnetized, induced onto the exciter armature. The exciter armature will produce AC voltage that will be sent to the rectifier bridge, rectified and sent to the main feed. Main feed will be magnetized, okay, and produces the magnetic field that will eventually induce EMF onto the main armature, where we will eventually take our output, our generator output from. Okay, so this is a coupled one. Now you can see this is the exciter feed winding. This is the exciter armature. You can see the diode plate that does the rectification of what comes out of the armature before it is sent into the field. Okay, then these two wire plus red and black is what will now be fed by the AVR. Okay, remember the AVR gets its output from its input from the output of the main generator. Are we getting it? So this is the AVR for the three-phase inputs UVW. Then this is the plus and minus, okay, to the exciter feed. So this is the completely coupled. You have the exciter feed there. Then you have your main armature, your main feed, the exciter feed and the exciter armature at the front. Okay. So this is what we have been discussing. You see, taken from the start point. This is the start point, which means that it is neutral. Okay. Then start point, this is one phase, second phase, and third phase. Okay. Then the taken to your AVR. Then from your AVR to your exciter feed. Then exciter feed magnetized, induced onto the exciter armature voltage that will now be fed onto the rectifier bridge, okay, that will convert the AC produced here to DC that will be fed into the main feed. So the main feed will now produce magnetic field that will induce into the main armature that will give us the output that we actually want. Okay, so everything put together is what we have here. So that's for the rotating exciter. So now the static excitation system that we talked about, like we said earlier, is made of electronic circuitry, okay, semiconductor devices that helps to convert the AC that comes into it into DC, as we saw in the case of the rectifier bridge on the rotating excitation system. So this is the main power panel that receives power from the excitation transformer, as we'll see later. Then here is the control panel, okay. So the output from this unit is sent into the main feed via these slip rings, as you can see here. Okay, so this brush and slip ring arrangement is what will take the power that is from this static excitation unit, okay, to the main feed itself. So now if you look at this is the excitation transformer. So the excitation transformer is connected to the output of the main generator, as we'll see later. So this will now step the voltage down to the excitation voltage, assuming maybe our main generator is delivering say 11 kV as an example now. Then this transformer will take it down from 11 kV to maybe 415. Okay, that 415 will be fed into this static excitation unit that will now be converted to DC that will be fed to the main feed of the generator to magnetize the main feed. Okay, so that is what we are seeing here now. So this is the slip ring arrangement. okay, that carries the power into the main feed. This is the main armature. Are we getting it? So from the output of the main armature, we feed the excitation transformer. The excitation transformer will feed the static excitation system, and then the static excitation system, in some cases, you have the thyristor rectifier. Okay, so as you vary the rate at which the thyristors they are fired, or the rate at which signals are sent to the gate of the thyristors, you will see that that will vary the firing rate and helps to control the voltage that is coming out. So the output voltage will now be sent to the main feed via this slip ring, okay, into the main feed. Are we getting it? So this is the schematic of the static excitation system. So this is the generator, this is the output of the generator, this is the excitation transformer that we saw earlier. Okay, so that excitation transformer fits the static excitation system. See it on the power rectifier. Okay, so the rate at which you fire these gates will determine what will be available here to the to be sent to the main feed by slip rings, okay, and brushes. Are we getting it? So this is the schematic. Okay, so here this is just for feed flashing in case the main feed loses the initial magnetism that is required to actually build up the voltage within the generator itself. So if that happens, you can flash to build the magnetism for the generator to start producing electricity. So everything put together, that is what we are having here. The diesel engine parts coupled to the alternator or the electrical part. So we have a complete unit, okay, to produce the power requirement for our facility.